In this next video, we're going to look at induced nuclear reactions rather than naturally occurring nuclear reactions. And this was relatively new technology as of 1934. So really before 1934, we didn't know we could do this. But around this time, it was discovered that we could use radiation. And we could use this radiation or direct it at other elements to basically change them. All right, and the most famous example of this, obviously, is the atom bomb, right? So in an atom bomb or even a nuclear reactor, we're forcing a nuclear reaction to take place artificially, and through that creating a tremendous amount of energy. All right, and there's a few different ways that we can change a natural element into an unnatural element. So in the example of the atom bomb, one of the atom bombs was made of plutonium, and that was made artificially. Okay, so what we could do is we could change a nucleus, or nuclei. Let me just change this. Nuclei is plural. So we could change nuclei to another stable nuclei. So a good example that they show you in the book was one of the earliest experiments was taking boron-10. And what you could do is you could have a sample of boron-10 and you could expose it to alpha particles. Whoops. And the alpha particles could come from some other radioactive source. And during this process, you could actually change boron to nitrogen. And so at the time, this was pretty wild, right? This goes against the law of conservation of matter. But it works with nuclear reactions, right? As long as things are balanced, meaning you account for this alpha particle on one side and the neutron on the other side, we aren't creating or destroying anything here. All right? So that's one unique purpose. Another thing that they noticed, though, was sometimes you can change nuclei to nuclei that are unstable. And what this means is that the new nuclei will undergo radioactive decay. So a good example of this that we actually saw in the last video was taking nitrogen, nitrogen-14 from the air, bombarding it with a neutron and creating carbon-14, and we said that that carbon-14 will decay slowly over time, right? So that's an example of this even occurring in our upper atmosphere. All right, there's two more that we'll talk about a little bit more later, but the first one is you could slam two nuclei together. You could fuse two different nuclei. And this process is called fusion. It's easy enough to remember. If you're fusing two things, it's fusion. However, there's also the opposite of this. You can rip a nuclei apart. And when this happens, this is called fission. Classic example of this is in nuclear reactors and atom bombs, right? And again, we'll talk more about that in our last video. Now, at the time, this was incredibly challenging, and they had to develop a lot of technology to do this. So let's talk about the challenges. All right, the first one has to do with neutrons. All right, so neutrons are a common source of radiation where we can use neutrons, like we saw in the example with cosmic rays. We use neutrons to convert nitrogen-14 to carbon-14. However, neutrons are like bullets. they really just zip past other nuclei very, very quickly. So neutrons must be slowed down in order for them to work well. In order for neutron capture to be effective. All right, and what they do to slow them down is they use something called a moderator. And a moderator is a material used to slow down neutrons. There's different types of these moderators, but they're commonly used in nuclear reactors, actually, in order to moderate the rate of the reaction, right? If you think about a nuclear reactor, you don't want an atom bomb going off. You want a slow fizzle of energy over decades that provides energy for a community, for example. So there's moderators that are used to slow down and temper that reaction. However, we often use moderators for other purposes involving neutron capture as well. All right. With charged particles, everything's different. So with charged particles, we have to overcome the repulsion by the nucleus. Whoops. We must overcome repulsion by the nucleus. Right? So you can imagine if we have a positively charged particle, it doesn't want to get close to the nucleus because the nucleus has a positive charge, right? And if we have a negative particle, it doesn't even want to go through the electron cloud because the electron cloud has the same charge, right? So the easiest way to do this is to speed them up, provide them with a large amount of energy. So this can be done by speeding them up and providing them with enough energy. All right, and there's a couple different ways you can do this, but they all involve something called particle accelerators. So I'll show you one of these that's pretty common. These have been around for quite a while. This one right here is circular. Okay, so in this one, we've got a circular system where we're using these strong magnetic fields to essentially start out with the particle in the center and speed it up using magnetic fields all the way until it ejects out an open port here. This is called a cyclotron. Okay, so that's one method we can do. The second one is just a linear accelerator. So this one down here, it's kind of the same idea. We're going to use electric currents to help speed up these charged particles and eject them through a series of tubes, and we'll fling them out essentially at a target. So this one is just called a linear accelerator. You may have heard about these in the news. In fact, there are some enormous ones, the size of cities almost, where we try to speed up these particles faster and faster and faster, and even smash these radioactive particles against one another to see what happens. That's when we get into really fancy physics. So if you heard about all of the new particles being studied at the cyclotrons in Europe, it's using similar technology, just very, very advanced, way beyond this course. So those are the two techniques that we are shown in our book. All right, the last thing is kind of this weird trivia. All right, so trivia, we can use this to make new elements. All right, so let's pull up the periodic table really quick. So I'm just going to use our TCC periodic table. And here's the cool thing. Before 1941, we had these holes or gaps in our periodic table. It wasn't until we started filling in the gaps using this sort of chemistry that we discovered that we could, in fact, make these elements that we predicted existed, but we had to use radioactive chemistry. So the first one that we discovered was technetium, number 43 right here. And then we discovered promethium, number 61 down here, using a slightly different technique. And then we discovered astatine, which is number 85. Let's see where that is, over here. So that one is also synthetic. And then we discovered francium, number 87. So that was one of the last alkali metals. So all of these were discovered between 1937 through 1941. So all of those were gaps. We knew something should go there, but we had to make them synthetically. So I should say actually discovered or created between 1937 and, that should be 1941. So kind of cool history trivia. The other thing too that's important to remember is that uranium, this is the heaviest natural element. Everything after uranium is synthetic. So everything heavier is synthetic. All right, and what these are called are the transuranium elements. So let's go ahead and block off all the transuranium elements. Obviously, it's going to consist of anything above 92. However, remember that this entire row is an extension of that. And in fact, this periodic table that I'm showing you here isn't quite complete. In fact, we've discovered these remaining blocks here. So if you look at a newer periodic table, that entire bottom row is now complete. Pretty fascinating stuff. Oftentimes when we make these super heavy elements, they exist for a fraction of a second inside some sort of particle accelerator, and then they quickly decay, but they exist long enough for us to detect, therefore we know that they're real. All right, I hope this helps. We have one more video, and then we'll wrap up this chapter.